Hello. Well, I thought of canceling my talk since I didn't come in first. Just obviously, I don't know what I'm talking about. So anyway, my name is Bond, Howard Bond, and for many years I was with the Hubble Space Telescope project down in Baltimore. I moved up here to Penn State a few years ago. So I just wanted to talk a little bit about taking images with the Hubble Space Telescope. If I took all the lettering off, we can see the Hubble Space Telescope as photographed by the astronauts. And first of all, just a few facts about Hubble. It was launched in 1990 aboard the Space Shuttle Discovery. Orbits the Earth every 95 minutes at an altitude of 340 miles. Astronauts have then revisited Hubble 5 times to service the telescope, most recently in May 2009. The Hubble telescope has a 94-inch primary mirror, and the instruments are 2 electronic cameras, which are actually very similar to the one that Evan described, and 2 spectrographs. Now, you may have read something in the news about problems with Hubble last month, and those were related to the gyros on board the spacecraft. So let me give you an update of this status of Hubble. First of all, there are reaction wheels, which are kind of large flywheels, and these are used to move the telescope by spinning up or down the wheels. In reaction, the telescope moves the opposite direction, and that's how we move and point the telescope. Then the gyros sense the rotation rate of the telescope and are part of the guidance system on the telescope. And then finally, once we're on target, we have the fine guidance sensors, which lock in on stars at the edge of the field of view and then maintain the pointing of the telescope during the exposures. The pointing accuracy that's achieved with the telescope is 0.007 arc seconds, which is a really tiny angle, and someone worked out that it's the size of Roosevelt's head on a dime at a distance of 200 miles. So we routinely achieve this level of pointing of the telescope. Now, there are 6 gyros on the spacecraft, 3 units which each have 2 gyros in them, and in normal operations we use 3 of the 6 gyros. And after the last visit by the astronauts, we had then 6 functioning gyros. And here actually is down in Houston, the astronauts practicing installing a gyro unit, which actually you can see is quite small. But those are part of the system that guide the telescope. Here are the astronauts actually up in space installing gyros in the space telescope. Now, so as I said, we had 6 gyros after the 2009 servicing mission. The first one failed in March 2014, second one in April 2018, and the third one failed last month on October 5th. So we were down then to 3 working gyros, one of which had been left turned off. And when it was powered up, it actually did not stay within the required specifications. And so there was an awful lot of hand-wringing, and the engineers then tried a lot of things, including literally turning it off and on, like you do with your computer or your cable TV. And this actually restored it to operating. Is that a question? Oh, yours. I'm not sure about that. In any case, that gyro was restored to operational range, and we are now on 3 gyros, and normal observations resumed on October 27th. So we were down for about 3 weeks. We're back to normal. And by the way, the remaining 3 gyros are less susceptible to the failure mode than the first 3 were. So right now we're operating on 3 gyros, and the plan is that when the next gyro fails, we'll actually drop to 1 gyro mode, which is actually almost as good as 3 gyro, but it does limit the amount of sky available at a given time. And we'll turn off the other gyro. We'll stay in we'll work that way until that gyro fails. Then go to 1 gyro mode on the last gyro, and when that fails, that's the end of the mission. The engineers tell us that the probability of still being in operation in 2025 is 80%, so we're pretty optimistic about this. And so we do expect to overlap with the James Webb Space Telescope for several years. Eventually, Hubble will re-enter the Earth's atmosphere probably in the 2030s. So if this works out, this will actually be 41 years after I first joined this project. So that gives you the time scale of these expensive NASA missions. All right, so anyway, I wanted to talk about some of the images and just show you some of Hubble's greatest hits to start off with. Here's one of our first images in the 1990s that I worked on. This is the Ring Nebula in Lyra. For many years, I taught college courses down at LSU before I moved up to the Space Telescope project. And you could buy these slides from the Palomar Observatory. Here's the 200-inch famous telescope at Palomar. And I, for many years, would show this picture, an actual slide before we had PowerPoint, of the Ring Nebula. So I was tremendously excited when we got our Hubble image of the same object. So I think these two slides show you why we put a telescope in space, to get the much higher resolution that's possible in optical imaging of objects like this. So that's the Ring Nebula. It was used on a postage stamp at the 10th anniversary of Hubble back in 2000. Sombrero Galaxy, one of our Hubble heritage images. I think you saw this one in the quiz a minute ago. This is one of the objects I worked on with Hubble. Color image of the light echo around V838 Monocerotis. And actually, this is the case where the star in the middle suddenly got much brighter for several months and sent a wave of light out at the surrounding dust. And so this is what we call a light echo. And we actually made a little animation over 4 years showing the light from this explosion moving out into the surrounding dust. Here's the center of the Crab Nebula, another famous Hubble image. And gravitational lenses, where these massive galaxies distort the light from a background galaxy. And so this is a highly distorted image of a background galaxy due to the warped space around these massive galaxies. Somebody pointed out the smiley face there, and here are these two massive galaxies distorting the background galaxy and making a smiley face in space. And here, oops, what's happening? And I'll just show you a couple of the most recent images. This is the Ghost Nebula in Cassiopeia. This is actually an infrared image, taken in infrared light with the Hubble Space Telescope. And here's the 28th anniversary image release, the Lagoon Nebula. And I don't know why these letters are overlapping. This was just released a week or two ago. It's a star cluster, not in our galaxy, but in the Large Magellanic Cloud. And due to the color rendition, you can see that many of the stars have evolved to become red giant stars. And so they're nearing the end of their lives. Now, probably the most common question when people look at these Hubble pictures is, are the colors real? And that's actually a very complicated question, which would take me probably an hour to go through in detail. But let me just make a few points that depends what you mean by real. And one basic point is that the human eye cannot see colors at low light levels. Like if you go outside when the full moon is up, everything looks kind of black and white. If you took a time exposure, you'd see that all the colors are there that you see when the sun is up. But the way the human eye works, you can't see colors at low levels. And so what we do is we try to show what the object would look like if the object were bright enough that the eye could see the colors. Another point is that Hubble can see ultraviolet and infrared light that our eyes can't see. And Evan went through this in some detail, but Hubble, just like the ground-based telescope here at Davy Lab, takes black and white images through color filters. And then in the computer, we have to combine those to make a color rendition. And another point is that the type of object we're looking at determines what its spectrum looks like. And that determines the imaging procedures we use. So quickly, some physics here. Kirchhoff's laws, which describe the spectrum of different types of objects. So law number one is that a dense gas or a hot solid or a hot liquid has a continuous spectrum, all wavelengths. If it's a thin gas, like for example a nebula in space, you only have certain wavelengths. We call that an emission line spectrum. So nebulae, like the Ring Nebula, have a spectrum like that. And finally, a star, or the sun, is the third Kirchhoff law, which is that there's a continuous spectrum from the deeper layers of the star or the sun, but then the sun has an atmosphere of cool gas, which puts absorption lines on top of the continuous spectrum. So, kind of a general rule of thumb with the Hubble images, or any astronomical images, is that for stars and galaxies, you can use a broadband filter to admit a lot of light, because basically you have a spectrum like this. But if you're looking at a nebula, what you want to do is narrow filters that just isolate an individual emission lines. So now Zsolt Levé, the master of rendering Hubble images, gave me several slides. So, for example, for galaxies, we can make what are approximately true colors. And what we do is we take, just like Evan described, through black and white images, through a blue filter, a green filter, and a red filter. These are black and white images. We then apply colors to the three images, which are approximately the true colors that those filters are transmitting, and then combine those to make the color image. And let's just zoom in on that. And not only is it a nice, beautiful color image, but there's some astrophysics going on here. For example, the blue light is hot, young stars. The pink is glowing hydrogen gas, where there's new stars forming. And the orange is old, evolved stars, red giants. And so we can see the different stages of stellar evolution in this picture, from young stars that are just forming in that galaxy on the left, to old, evolved stars nearing the end of their lives in that galaxy at the lower left. Now, on the other hand, when we consider a nebula, which only emits selected wavelengths, we generally use a false color rendition. So here is the Eagle Nebula, and we use three narrow band filters, which isolate light from sulfur, hydrogen, and oxygen. Now, as the wise astrophysicist over here points out, that the true color of H alpha is red. But the problem is the true color of the sulfur is also red. So slightly red, but all practically the same color. So we were forced to go with a false color rendition and make the hydrogen light green to make the final composite image. And let's just zoom in a little bit to see what this final image looks like. But again, these are now not true colors, but showing where the different chemical elements are emitting light in the nebula. Coming back to this one of my favorites, of course. This is, we use broadband filters, so this is approximately a representation of the colors you would see if the human eye could see light, these low light levels with our color vision. In other words, if we could somehow magically make this object brighter, these are roughly the colors we would see. And indeed, the star at the middle is a very red star. It's a very low temperature star, as this color image shows us. Here's another one of the images that I worked on. Again, these are broadband filters, so an approximation of the true colors. And later on, I could explain to you why we have these blue arcs in this image. But let's move on back to the Ring Nebula. This is a false color image, and it shows a number of physical properties of this object. First of all, this little speck here is this very hot star that ejected its outer layers. A star more or less like the sun that reached the end of its life, ejected its outer layers into space. And then the blue represents helium, which requires a very hot temperature. Yellow is the oxygen, cooler temperature, and red at the outer edge is nitrogen. And so we actually are seeing the range of temperatures in this gas around this hot central star. And then just to conclude, 3 years ago now, there was an internet contest to vote for the best Hubble image. And it came down to the final two. So here was my light echo image, and here was the Eagle Nebula, and I came in second. But I was still happy to have made it, or had my image, the Hubble image of this object that I worked on, made it to the final face-off. So, thank you. Well, there. Oh, hi.
For the light echo photo, how long of what was the total light integration time for that photo? How long did you have to expose for?
I'm trying to remember, each time we came back to the subject, I think we spent one Hubble orbit, which would be, now of course the Earth blocks the view half the time, so it'd be about 45 minutes total in the 3 different filters. Oh, and the question had been, what was the exposure time? Sorry.
So, how did you know to look at this object? What made you decide to look at this star?
The outbursts of the star was actually discovered by... Oh, the question was, what made me look at this? The outburst of the star was discovered by an amateur astronomer in Australia. And at first, everybody thought, oh, it's just another nova, ho-hum. But then an astronomer at the Naval Observatory, I believe, in Flagstaff, discovered the light echo. And then we thought, oh, wow, this is going to be cool. So we got the Hubble telescope on it, and we got that series of images. And that taught us all kinds of things about... For example, since we know the speed of light, you can use the light echo to determine the distance to that star. It turned out to be 6,000 light years. So we actually... That told us that that star temporarily was one of the brightest stars in the Milky Way. And then later on we asked, well, what made it get so bright? And we think it was a case where 2 stars actually collided and merged to make one star, releasing a tremendous amount of energy.
So I've got another question then.
Another question.
So these images of nebula that we see, they're very incredibly colorful. If one of these nebula was as close to us as like the nearest star, like Proxima Centauri, would we be able to see these colors? Would this actually look anything similar to this image? Would we just see a big bright object in the sky, or like how bright would these look and what would they look like?
Well, I kind of tried to partially explain that, but first of all, the human eye, as I said, can't see color at low levels. So, no, you wouldn't be able to see those colors unless you had some way to amplify. If the human eye had the capability of taking a long exposure, which it doesn't, you could see the colors. Another point, I didn't go into this, but surface brightness does not depend on distance. So, even if you got closer to this, the surface brightness wouldn't be any higher. So, people have the idea, well, if I could go closer to this, maybe that would make it brighter. It does make the stars brighter, but not the extended object. So, no, it wouldn't look like that unless you had a way to take long exposures with your eyeball.
Power to go.